Good evening, everybody. This is Bob DeVance, K5CRX for the McKinney Amateur Radio Club. This is actually session number 5 of our series for the general licensing class. As we're trying to cover the technical subjects for that particular exam. We'll have one more session after this as it's scheduled. Unfortunately, I was really down with the flu last week, so we missed that week. So tonight we'll discuss whether we want to do a makeup session along the way as well. We do have some time. I think we could do that. Our goal along has been to finish next Thursday afternoon, Thursday evening rather, and then on the following Sunday, the club would be giving the exam, of course, at the Heard Museum on the third Sunday, as is always the case. So we were trying to put this in concert with the timing for that as well. So we'll see what everybody wants to do tonight on that one. For tonight's sessions, okay. So again, this is our information. It has my email address, phone number, etc. on there in case anyone would like to contact me for whatever reason. And that's our list of subjects. We had finished up receivers last time. We started on transmitters because we had just a little bit of time left, and we went a few slides into that, and we'll decide later if we want to start back at the beginning or if we want to pick up where we left off, because there is a lot of information in this particular series of slides. So that's the agenda for tonight, and we'll see what everybody wants to do as soon as everybody gets signed in and we're ready to go. We'll be back online here in just a moment. Okay, for tonight, we were scheduled to pick up transmitters again. According to the note that I had, those 93 or so slides, and by the way, I've added a couple more that I thought would help, but we had stopped at slide number 30. We actually were going through all the descriptive material. And so we can either go back and start at the beginning of that, which might not be a bad idea since it's been 2 weeks ago, and just go all the way through. I think we can go through it in one session, I'm sure, tonight without a problem. Do you guys have a particular druther on that or what you'd like to do?
It seems to me we went through that rather quickly, so I'd be okay if we revisited that again.
Be okay with that? Okay. All right. Good enough. Then that's what we need to know. Let me stop the share, and I will bring up the other sharing and share again. And this time we're going to share that one. Share. And we're going to start at the beginning and go for it. Okay. Am I looking okay there on the screen for you guys?
Yep.
Okay. So that's the advertising thing, as it were, there. Oh, my. Oop. I'm trying to hide the meeting controls again, and they've got a long-winded thing for that. Okay, let me get it rolling here. Working with the HF transmitters, there are quite a few questions in this, so I think probably going back for review really is a good idea. I have it set so I'm only seeing the slides. I don't see your faces. So if you do have a question, just hop in there with the audio and say, hey, what about this? And we'll certainly take a pause and talk about anything that you want to. Okay, instantaneous power level of a signal varies with amplitude modulation. Amplitude meaning the height of the wave. I've added a little further down in the questions a couple of pictures of that, and it will illustrate that further when we get to it. But for AM or amplitude modulation, we're just varying the instantaneous power level of the signal itself. Balance modulator is used to produce a double sideband carrier, or a double sideband signal rather, with a suppressed carrier. And if you'll recall, within sideband, single sideband, the reason we call it that is in AM we have double sidebands plus a carrier. In single sideband, we suppress the actual carrier so that it doesn't get transmitted, and then we filter out or we suppress one of the sidebands, either the upper or the lower, as we select it, and filter it out so that only one sideband is actually transmitted. The balance modulator is the culprit that allows us to pull those two sideband signals out of that, modulated with information. Just a picture of it there. Input modulation signal over on the left would be your microphone. Carrier signal as some sort of an oscillator or whatever going through the balance modulator comes into a filter. At this balance modulator, we come out of that and we have the two sidebands, and then we filter one of the sidebands out, so we're left with either USB or LSB, lower sideband, upper sideband, and it goes toward onto the output for amplification and to go to the antenna. Okay, an impedance matching transformer lets us match precisely the radio stages to present the desired impedance to the transmitter and the feed line. Okay, you'll remember that when we're doing an impedance matching transformer, which is usually what's in an antenna tuner, we're setting that desired impedance of the transmitter to match the feed line. We're not actually changing the impedance of the antenna or the match of the feed line to the antenna. That mismatch is still there, but we're setting up the match between the transmitter and the feed line, which helps to minimize losses and give us maximum power transfer, at least into the transmission line itself. Balance modulator. Balance modulator gives us the upper and lower sidebands. Carrier is suppressed near zero. And as we said, we filter out one of those, either the upper or the lower sideband. And the answer to that particular question is a filter, which is what's used to cancel out the unwanted sideband, a filter. The phone emission using the least bandwidth of the ones that we use is the single sideband for audio, that is. Now, of course, CW is much less, and those the digital modes are less even than that. But for voice modes, single sideband is the best. Takes about 2.8 kilohertz of bandwidth to transmit on single sideband. In the rules and regulations, there's also a question in there dealing with how close to the edge of the band can you get and be legal. So we have to take this into consideration. For example, on 40 meters, we go up to 7.300. So if you set your transmitter at 7.300, you would be illegal because your signal would go from 3.00 to 7.300 to 2800 added to the end of that. So you'd be 2800 hertz above the actual band edge is what we're saying. So generally, rule of thumb is we stay 3 kilohertz away from the band edges, and that applies to the lower edge or the upper edge. That just keeps us safe and makes sure nobody yells at us for being out of band when we transmit. So the 2.8 kilohertz is the key there. The single sideband uses the least amount of bandwidth at about 2.8 kilohertz. Another picture of a transmitter block diagram. Then this particular one is a upper and lower sideband transmitter. Mic signal comes in on the left. An amplifier for the audio comes in. We hit the balance modulator, and then we have both of the signals being generated there, both the upper and the lower sideband. But the balance modulator kills the carrier frequency that would normally carrier signal that would normally be mixed with that, and leaves only the upper and lower sidebands on its output going into the crystal IF filter. Crystal is usually abbreviated with an X, by the way. So then that crystal filter will filter out whichever sideband we don't want, leaving us with an intermediate frequency, an intermediate level frequency. We amplify that, mix it, step it up again, getting closer to where we want. Finally, we get to the final mixture that's mixed with our signal from our variable frequency oscillator to give us the actual output frequency we're looking for through our power amplifier, and then finally on its way out to the antenna. So a lot of different things going on there as we go through this. This, as I said, is showing the upper and lower sidebands. If it were AM, we'd have a different modulator there and a little bit different circuit between the mic amp and the crystal IF filter. But for right now, they're trying to show single sideband. Speech processors are something with which to be aware. If you get too much speech processing, they sound like garbage, basically. If you put a little bit in there, you could increase what appears to be the loudness of the transmitted signal. Basically, it increases the average power of a single sideband signal. Doesn't actually increase the power per se, it just increases the average power. And if you get too much on it, then it obviously starts to have a problem. So we have to watch doing too much speech processing on single sideband. Okay, turning on the speech processor does not increase the PEP or and I just went blank. Peak envelope power. I couldn't get what PEP stood for. Peak envelope power, if you're 100% modulated already. It'll increase the average power, but when it does that, it will tend to remove the bass from the audio, making it much more tinny, which can be good, not unlike CW. The higher frequency sounds tend to go through the air better and are easier to hear and recover on the other end than something that's real bassy. So sometimes that will actually increase the signal readability, but it can make it sound like it's too hot. It sounds like you're over modulating or over driving the microphone. It sounds like you have a mouthful of mush. Stay off the speech processor button unless necessary is good advice. Okay, talking about automatic level control or ALC controls. Acts like a throttle or a governor, if you please, to transmit for the transmit power so it can back off the transmit power to keep us from overdriving our output circuits. If we have our mic gain set way too high or we're doing too much processing with it, or if we're doing digital and we're driving it with a computer signal and that signal is set too high, we can overdrive it, in which case we need that ALC or automatic level control circuit there to govern it back and adjust the power back so that we don't destroy our transmitter. There's on most radios, there is an ALC meter that you can select and you can see what the automatic level control is actually doing if you want to monitor that. If somebody says you're sounding garbagey, or if you're watching the ALC meter and it starts to go up too high, back off on the mic gain a little bit or cut the drive from the computer down just a little bit, and that would normally resolve it. ALC jack on on your transceiver also goes to a linear amplifier if you're using a linear amplifier. You remember that a linear amplifier is a high power amplifier that our transceiver transmits into. It's called a linear amplifier because the signal coming in comes out the output jack essentially the same as the input. It's just stronger or bigger. It does not distort the signal on the way through, hence the term linear. At any rate, the linear amplifier has to have a handshake with our radio that's driving it. And so it takes a little bit of time, make sure everything is straight. And we'll get into another question there about timing for this a little bit later. But for right now, we're talking about not overdriving the radio. If you're overdriving the radio and that signal comes out, it's just going to be amplified and splattered through the amplifier. So the signal gets distorted due to excessive drive once again if it's going through the ALC. Now, many of the output amplifiers have their own automatic level controls as well. And can help to regulate that. If you overmodulate on high frequency or HF, you're going to spread your signal over a wider bandwidth than a properly modulated HF signal. We call it splattering. If we looked at that on a spectrum analyzer, we would see the main signal that we're transmitting on, and then multiple little smaller signals either side of what we're targeting, where that splatter appears. It's just garbage, adds noise to the band. If we're splattering, turn down the mic gain, turn off the speech processor if we're using that in order not to be pushing our transmitter harder than it can handle. Good check for that, of course, is just ask the other side, but how do I sound today? If sound is good, then you're probably okay. Most newer high-frequency transceivers do have a speech processor button to turn it on and off. And the West advice is turn it off. Brings in excessive background pickup, cause your signal to sound distorted, and can cause excess intermodulation, in other words, splatter. So that's one of those all of the above answers when you get to that question. Speech processing gives excessive background pickup, challenge signal to sound to be distorted, and causes splatter. If you have excessive drive or the speech level set in an amplified modulated, an AM, in other words, phone, single sideband transceiver, your signal will sound distorted if you're driving it too hard, as we said. The This is an AM we're talking about now. The signal waveform shown on an O-scope has the top clipped off, so it has a flat top. And there is this little picture that I picked up there in one of the other places that shows that on an O-scope. You see the display on the scope there. Instead of that sine wave being rounded at the tops and the bottoms like it should be for a nice, pretty sound wave, the tops of those are clipped off, which makes it very, very distorted. It's called flat topping is the common term for that. And we want to stay out of that. If we push it too hard, then we can get the flat topping and we'll be very garbagey sounding and distorted to somebody else. Usually the other side will tell us that right off. Okay, faithful reproduction of voice over single sideband depends on the equipment linearity, meaning it's that whatever goes into it is faithfully reproduced on the output. New digital signal processing techniques for modulation, plus a lot of different other add-ons and special mics and such help us with it. There's a two-tone test oscillator we can use to allow us to test a single sideband transmitter. We send two audio tones into the input or into the mic input, and we observe the output on an O-scope and see if they come out like they went in, basically. That's called testing the transmitter's linearity, seeing if the transmitter is linear, meaning whatever signal goes in is what is the signal that comes out, but just amplified. Okay, two-tone test generator. We'll have another question on that. There's a little bit more about that. Of course, as Gordon says here, the best thing is just ask fellow hams how you sound. If they say you're doing good, then you're going to be linear. You won't have a problem. If you're going to service your own equipment, there's a little box sometimes called a wobbler box. It will generate two non-harmonically related audio tones for testing, usually 700 and 1900 hertz each. The device will have an output where you can plug it into your transmitter mic input, or many have a little speaker. You can just key the mic and hold it next to the speaker. The two tones are not harmonically related. That is, one is not a multiple of the other. And you listen to that. You can listen to that on the audio CD. If you get Gordo's book that has the CD with it, you can actually hear that and see what it sounds like. Which ultimately you look at it on an O-scope to see what it physically looks like. Single sideband is the primary mode, the predominant mode in the phone bands, of course. Still a lot of other activity down in the AM areas. There's some special spots in the frequency spectrum where people tend to do AM particularly. The envelope of the AM signal is the outline or the extreme outer limit of the radio frequency signal. Now, I've got pictures of that. I'll show you that again in just a little bit. 100% modulation is defined when the peak envelope goes to zero. During the negative modulation peaks, increases to twice the amplitude of the unmodulated RF carrier. During the positive peaks, I'll show you a picture of that in just a minute, which I think it'll make more sense. The human voice, though, of course, is very asymmetrical. That is, it's not regular in its peaks and valleys. So the positive, negative peaks can be very, very different and very hard to detect. We have some fancy circuitry these days, though, that will tend to average that out and give us a good sounding signal. So standard practice, been adopted by many dedicated amateur operators. People just like AM. If you've never listened to AM as compared to single sideband, it is quite a treat. The audio generally will be crisp and clean and sharp, much more so than the single sideband signal will be. It's kind of like the difference between listening to an AM radio on the broadcast band when there's static and a good strong FM signal on FM radio, which has no static. It's somewhat compared to that. And I'm just keeping rolling. If you have a question, be sure and tell me. An O-scope is the test equipment of choice to look at the output of a radio. So look at the output signals. Don't buy one unless you plan to do a lot of circuit design, and that's generally true. Of course, nowadays you can get a decent little scope for under $100. That used not to be the case, but an O-scope is a very handy tool for seeing what's going on in any kind of a circuit. You can check the mic output of the mic amplifier, et cetera, is all the way up to the output of the actual radio itself. The O-scope has horizontal and vertical channel amplifiers, meaning it has amplifiers to move the signal from left to right as you look at it, and it can move it up and down the vertical channel to give you a good display as it moves left and right so you can see it. The O-scope has horizontal and vertical channel amplifiers. Picture of an O-scope there for you, just FYI. Magazine editors review the waveform of a CW signal or its two-tone test. Of course, they'll use an O-scope. That particular O-scope is just showing an AC sine wave on it with a little bump on the side. You can see the vertical amplifier controls, the horizontal amplifier controls, as well as some other controls that are just inherent in that. That's an older Tektronix scope. One of the goodies there, that's about a 1990 to 2000 vintage O-scope, but there's just literally dozens and dozens of those around. I have a couple that are very similar to that. They work forever. Okay, we take the attenuated RF output of the transmitter, couple it to the vertical input of the scope so we can see what the signal looks like. Check the quality of the signal. When we talk about the attenuated RF output, what we're talking about is taking the output of the radio, which may be 100 watts if it's full power. You can't put that directly into the input of the O-scope. It'll burn the input channel out. So we put it on what we call an RF pad, which is nothing more than a dummy load, really. We put it into the dummy load, and then we have a little takeoff that will take a little sample of the RF from that we can put into the vertical input of the scope so we can actually see it without destroying the input channel on the O-scope. So the attenuated output it goes into the input of the O-scope. Has to be attenuated or it will blow up the scope. When you whistle into your single sideband microphone and look at the resulting waveforms on the scope, you'll see that only the O-scope can show you what it really looks like, can really show the complex voice waveforms. You'll see your voice go all over the scope when you do that. Tube types. Tubes used in many of the amplifiers still today. After new tubes have been installed in an amplifier, follow the steps in the instruction manual to neutralize the circuit. That will eliminate the possibility of self-oscillation. All tubes have a small amount of capacitance between their elements inside the tubes. And we have external circuits that work in conjunction with those different elements in the tube to neutralize or cancel out that capacity so that we don't self-oscillate, so they don't generate their own signal when there's no actual input into there. So neutralization eliminates self-oscillation. Okay, picture of AM and FM signals here, which are pretty good signals, really. Modulation that changes the frequency is frequency modulation. Modulation that changes the amplitude or the height is amplitude or AM modulation. So at the top of the picture, we show an information signal, just a modulating sine wave. The carrier frequency before it's modulated is just a plain old signal going straight across. And then when we impose the audio modulation and AM, you'll notice that the signal bounces up and down in concert with that audio modulation. But the FM signal, by contrast, does not change strength. It does not amplitude modulate at all. Instead, it actually shifts in frequency. The amount that it goes back and forth is called frequency deviation. Most of our FM transmitters, like our 146.52 and VHF, UHF transmitters, most of those use plus or minus 5 kilohertz deviation, as it's called. We allow the transmitter circuitry to change the frequency by plus or minus 5 kilohertz. That's normally the maximum deviation that we would see. But anyway, that is a picture, a representation of what the carrier wave looks like when it's frequency modulated. Okay, how do we get the frequency out that we're looking for in our HF rigs? If we're working on our local repeater here, 146.74, we're not likely to have an oscillator inside the radio that's going to generate 146.74 for a frequency for us. Instead, we use a much lower frequency oscillator because it's easier to control, it's easier to govern it and make sure it stays on frequency. And normally the convention is to multiply that local oscillator frequency by 12 in order to get the output frequency that we're looking for on VHF. That's just kind of the accepted standard that we use. So then we have a multiplier, which will take that frequency that the lower frequency oscillator is generating, and it will multiply it by 12 by selecting a harmonic of the signal. And then that signal will be used to generate the actual frequency or signal that goes out the transmitter along the way. Harmonics are like chords on a piano, if you like to compare it to that. They're mathematically related. Their tip here is it's logical that the stage of the transmitter is called a multiplier. The choice is the one that's mathematical, as in multiplier. So we're taking a lower power, lower frequency oscillator and multiplying it by 12 to the 12th harmonic to get the frequency that we want. We'll play with that one some more a little bit later on. Okay, on this particular question, they're asking us about total bandwidth of an FM phone transmission. How much bandwidth does this FM transmitter take up when we transmit? When we key our little handheld transmitter to key the repeater, what is it doing? Okay, if the deviation is 5 kilohertz, which we said is the maximum deviation that we normally would set, and we have 3 kilohertz audio modulating, which is 3 kilohertz is about the top of the vocal range. And that's the modulating frequency. We take the sum of those two, which gives us 8 kilohertz, multiply times 2, which gives us 16 kilohertz of total bandwidth. Now, let's see, a little note about that. Yeah, a lot of times we have places we can check it. We have instrumentation that can measure the frequency deviation. Of course, we can do that as well. And then once we know that and know the frequency that we're modulating with multiplied by 2, then we know we can tell what the total bandwidth is. And there's a name for that convention, and it escapes me right now, but I've got it further down in the notes. We'll come back to it. Deviation of any FM transmitter is increased when you follow the oscillator with a frequency multiplier. That's what we were just talking about. In fact, the deviation is multiplied by exactly the same factor as the radio frequency. So if we multiply oscillator frequency by 12 to get the final output frequency, deviation is multiplied by the same amount. So we would modulate a lower frequency oscillator, but that deviation also gets multiplied by 12 as we go up. So if what we're looking for here means the final deviation is 5 kilohertz, we can divide that by 12 to come up with the required oscillator deviation. So a 12 to 5,000 is 416 hertz. That's just kind of a simple calculation, basically. So we would modulate the oscillator with 416 hertz deviation, and then it gets multiplied by 12 to give us the 5 kilohertz deviation out the antenna. A reactance modulator produces FM, a frequency modulation, when applied to an oscillator. Phase modulation, if applied to a subsequent amplifier stage. Reactance modulator key to FM and PM phase modulation. Modulation that changes the phase of the RF wave is called phase modulation, as you would probably guess. I guess that makes sense, doesn't it? Or PM. Efficiency of an RF power amplifier, calculated by dividing the input power, dividing the output power by the input power. What that means is we look at the output stage, the final output RF amplifier. It's being driven by another intermediate power amplifier, which is generating so many watts. In their illustration here, they're saying the output of the transmitter is 100 watts. But it has 250 watts of DC on the input power driving that final transistor. So only about 40% of that 250 watts is actually making it out to the antenna jack, which means the efficiency is only about 40%. So 100 divided by 250 is 0.4, which is about 40%, which is fairly typical. So we don't get 100%. That would be kind of nice if we did, but we don't. Just doesn't happen. Let's see then. The caution down in the middle of that slide. Caution unless you have a rather uncommon peak envelope power meter, PEP meter. Now, they say that. I don't totally agree with that. A lot of us have PEP reading instrumentation. It's just a matter of flipping a switch whether you want average power or peak envelope power, and it will read it for you, and it'll give you a good reading. So that can be updated. Anyway, it's hard to determine the power using your speech or whistling or whatever if you don't have a way to measure it with a meter. You must use a CW carrier. Single sideband transmitters have a tune function, especially for that. When you tune your single sideband, if it has auto tune, it'll kick the CW while it's doing the tuning. which is continuous wave. The peak power of the human voice can be over 6 times the average power. Typical peak RF output power, as well as DC input power, can be many times what your slow-moving meter can indicate, which is why they're saying it's more difficult. However, if you put a steady whistle or a steady tone into the single sideband transmitter, and you do have a PEP reading meter, you can get a very accurate reading of what your power out is of that and measured in PEP. Okay, another question. Take half of the peak to peak voltage to obtain the peak voltage. You remember when we talked about AC, peak to peak, it's from the very top half of the sine wave to the very bottom half of the sine wave. So we're taking half of it, multiply by 0.707, which is the square root of 2, and then square that result, multiplying it by itself, dividing it by 50. There's a formula for that, as you can probably tell, and I'll show you the formula when we do the question. And then your calculator keystrokes, you go 250 times 0.707 is 176.75 times itself is 31,000 divided by 50 is 624.81. The nearest answer on the test is 625. And that may be one, rather than think about it, you just memorize the answer. That may be simpler. An unmodulated carrier is simultaneously peak and average. So if there's just the carrier going out, the peak and the average are the same, meaning it has a ratio of 1.0. And then there's another question related to that says if we have 1,060 watts peak, I believe it is, and what would it be on average if there's no modulation? And it would be the same signal, but it doesn't change. It'd still be 1,060 watts. Okay, transmitters used to be limited by DC input power to the final amplifier stage or stages because of means of measuring the RF output, which are now more readily available than they were then. We're talking primarily back in the tube days then, when that was being done. But now we have accurate peak reading RF power meters to do that. And this is the key. The limit on transmit power is 1,500 watts PEP, peak envelope power, output from the transmitter. It's PEP output from the transmitter's output jack. Uniformly applicable to any mode of operation, whether you're in sideband, CW, AM, whatever. 1,500 watts. Peak envelope power is the max out the transmitter jack, or antenna jack. A steady carrier illustrates both peak power as well as average power. If your watt meter reads, there's the question, reads 1,060 watts average, it'll read 1,060 watts peak as well. They'll be the same. Decibels again. Decibel is used to describe a relative change in power levels, a measure of ratio from one point to another. A 2 times increase results in a 3 dB change. So if we have 2 times, if the signal is doubled in strength twice, that would be 3 dB change. Likewise, if we halved it, it would be minus 3 dB change, going in the negative direction. And then we talk about different kinds of amplifiers. Now, the Class A amplifier, which is the purest and the most linear, the Class A amplifier is set such that it operates in the linear curve region of its output device, whether that's a tube or a transistor, meaning that it keeps the signal pure and honest. What goes in is what comes out, just amplified. And we can get to a Class B amplifier, a Class AB amplifier, a Class C amplifier, and then there's a couple of others out there for the digital world. But the Class A is the most linear, and the one will have the least amount of distortion, but it's also the least efficient. Maximum efficiency on a Class A is 25% when it's operating where it's supposed to, as low as 0% under no signal conditions. The Class A amplifier is always dissipating heat, whether it's putting out any useful signal power or not, because it's always on. So the Class A amplifier, like we would use for an AM signal, is putting out its maximum power even if there's a signal there or not. We have to watch that with our digital world, because normally digital works by modulating a CW tone or doing quadrature modulation on a CW carrier, rather, not tone. And so have to watch not to burn up our radio, because it is running 100% in Class A mode. The Class C, though, is ideal for high efficiency, nonlinear amplification of FM. Now, remember when we're doing FM, we're varying the frequency back and forth. We're doing nothing to the amplitude. All of our intelligence is related to varying the frequency. We can vary the frequency and distort the signal somewhat, and it doesn't hurt our ability to recover the data with great fidelity. So the Class C is good as a good high frequency nonlinear amplifier. It also worked for CW as well as FM. Single sideband or double sideband, where we do not need to distort it, would not work with a Class C amplifier. It will distort the daylights out of it. So Class C amplifier is used for boosting an FM transmitter's modulated signal or a CW signal. Okay, about the code. Smaller CW only transceiver operating Class C gives high efficiency, little battery drain. Class C equals high efficiency. That's the key to that particular one that they're talking about for that question. Linear amps will pump up your output waveform exactly as it appears on the input. That's why they're called linear. Not wise to run any linear amplifier on an HF mobile or on a simple home antenna until you're experienced with your equipment and discovered what 100 watts can do first. All they're really saying is linear amplifier pumps up your signal. Be careful if you're not familiar with it, and experiment with your 100-watt radio first to be sure it does what you want to do and whether you need an amplifier to go with it or not. Personal choice, by and large. The load control on an old power amp, seasoned hams will tell you to tune for maximum smoke. And of course, that's not really true. We kid about that. We say electronics no longer work when you let the smoke out. And of course, that's usually true. If the smoke gets out, that means something burned up. But what we do with the tube type equipment, which is what we're talking about when we say old power amplifier, we're talking about tube types. We tune for the desired power output without exceeding the maximum allowable plate current of the tubes that supply the output power, and making sure at the same time we don't exceed 1,500 watts output at the transmitter jack, or at the antenna jack, rather. So tune for the desired power output, get as much as you can without exceeding what the tube is capable of handling so you don't burn the tube up. Vacuum tube amplifiers operating properly when tuning is adjusted for a dip or minimum current. Unloading is such that the plate current at the tuning dip is at its rated value. And all that is to say is when you tune a vacuum tube amplifier, you tune it for a dip in the plate current and a peak in the grid current. And I don't think that's on the test anywhere. Just remember that you tune for a dip or for minimum current in the plate when you're tuning. Okay, tuning once to always be checked for the dip. Also, if you, especially with an amplifier, if you change several kilohertz, you generally need to retune with those type of amplifiers. Timing is important. We mentioned this a little bit earlier. When we key down our transmitter and it goes to our amplifier, there has to be enough time delay in there for the amplifier to come up to speed. If there are mechanical relays that switch it from transmit to receive or receive to transmit, there's a little bit of time for those mechanical relays to switch. And so there has to be some timing in there to take care of that. Most well-designed transmitters will delay the RF output until the mechanical relays in the transceiver and the external power amplifier are fully activated. So it's built in. And in the older world, old days, old world transmitters, tubes, and all that, where we didn't necessarily have that, you just had to be aware of that. And when you key down, you wait just a second for everything to switch, and then you go ahead and transmit. Or if you were really back there, you actually had a physical mechanical transmit receive switch, and you'd flip the switch to transmit, then you could transmit. When you finished, you'd flip it back to receive so you could hear what was coming in. Okay, new transmitters have the delay built in so they don't destroy anything. Now we're ready for the test. Anybody need to get a sip of water before we head into this? Here we go. I'm sorry, go ahead.
I said I'm good.
Okay, then here we go. What type of modulation varies the instantaneous power level of the RF output signal? And go ahead and answer the questions if you would for me. What changes the amplitude of the output signal? Which type modulation?
Amplitude modulation, D.
Yep.
Exactly. Output produced by a balanced modulator is guesses.
So the D again?
Yep,
Yeah.
double sideband. So we take the double sideband and we filter out one of those sidebands so we get the one we want by a balanced modulator. A reason to use an impedance matching transformer at the transmitter output. Well, I think we can rule out A pretty quick, can't we? Present desired impedance to the transmitter and the feed line, reduce the power supply ripple, and to minimize radiation resistance. No, we want all the radiation resistance we can get to put it out there. How about B? Would you believe B? Now, that's a little tricky. To present the desired impedance to the transmitter and the feed line. So we're putting the balance between the transmitter and the feed line. When we use a tuner, an antenna tuner, it goes between the transceiver and the antenna feed line. So we're actually balancing or giving a one-to-one SWR between the transmitter and the feed line. At the other end of the feed line, where the antenna is, there is still a mismatch, but we don't let the transmitter feel it because we match it at the point where we go into the feed line. That's what that question is really trying to say. Present the desired impedance to the transmitter and the feed line. We can do that with the transformer, of course. Often that'll be a toroid, the little circuit, little donut-looking iron core transformer. What circuit is used to select one of the sidebands? The balanced modulator gives us both sidebands. What filters out one of them?
A.
What
Filter
filters?
D, right?
Filter, exactly. We filter out one. Both sidebands come out of the balance. Only one gets through the filter following it, either the upper or the lower, depending on what the filter is set to do. Okay. Which of the following phone emissions has the narrowest bandwidth? What do you think?
That one's A.
I'm sorry?
A.
Absolutely. Absolutely. Vestigial sideband is a TV signal, by the way. Phase modulation, frequency modulation, if you remember we said a while ago, we use about 16 kilohertz, much wider than the 2.8 kilohertz we use for single sideband. Purpose of a speech processor. And I'll give you a tip on this one. The tip on that one is the word apparent.
A.
Exactly. It doesn't actually increase it. It makes it appear louder. It makes it appear more distinct. A speech processor affects the single sideband phone signal.
It increases peak power, doesn't it?
Average power. It's average. The peak does not change, but the average power, the amount of power distributed between the peaks, will increase somewhat. That's what gives it what looks like a high frequency response, or peaks the high frequency response, and removes some of the low frequency response. Is the way it amplifies between the peaks. What control is typically adjusted for proper ALC, automatic level control settings on an SSB receiver? So what can we adjust that would keep us from overdriving our transceiver? What things?
Transmit audio mic gain.
That's it right there. Turn back our audio, turn back our gain. Or if we're feeding it with a computer, turn back the data feed off the level for the computer. Why is automatic level control used with an RF power amplifier? What you think? Would you buy C?
Yep.
Reducing or eliminating distortion or reducing harmonic interference. Questions with answers similar to that are that's generally going to be the answer. Going to be one to reduce distortion or splatter or frequency interference. Which of the following is an effect of overmodulation? If we overmodulate the signal, it doesn't stay in the center where it belongs, but it splatters on either side. What would we call that splatter?
Excessive band drift or bandwidth.
Exactly. We'd see little spurious signals on either side of our target signal. What is the effect of an incorrectly adjusted speech processor?
All the above.
All of the above. You got it. It can do all of that. What is meant by the term flat topping? And that's where I showed you the little pictures there a while ago on AM, or amplitude modulation. What does that mean?
C.
Exactly.
Distorted by excessive.
We're pushing it with too much drive. We got too high level of speech, and we're causing the tops of the thing to be clipped off. Top of the sine waves are clipped off. What transmitter performance parameter is used for the two-tone test? I can't say that. What does the two-tone test prove?
Isn't linearity?
Exactly. We put two tones of different unrelated frequencies into it, and we observe the output, and those two tones should come through basically unaltered. Or that is to say, they will be linear. And we do that primarily with sideband. We use the two-tone test. Okay, what signals are used for the two-tone test? Actually, I put a cheat note in the bottom of that. You can read the answer right off there if you want to.
Ensuring 1900.
Now that's the two standard tones that are most often used, 700 and 1900. Yes. Mm-hmm. That's just a little box that'll generate those two frequencies and give you a nice clean generation. A little speaker there so you can put your mic down by it, or you can actually jack it into the input on your mic input on the radio. And then when we do that, the two tones that were put in there are not related to each other harmonically. That is, we wouldn't use like 700 hertz and 1400 hertz, or 500 hertz and 1000 hertz, or 500 hertz and 1500 hertz. That's why the 700 and the 19 they're not related in any way. Two non-harmonically related audio signals. Okay, these were a couple of slides that I added in here because I felt like they did a pretty good job of explaining what the things that we've talked about. On the right-hand side, on the modulating signal, that's just a 1 kilohertz sine wave generated by an instrument of some kind, probably. The carrier signal, which has been generated by another oscillator of some sort, is 10 kilohertz, and you can see it just going up right along its way there. Then if we put modulation on top of that, an AM signal, you'll notice that the top half of C there, the modulated signal, the top half of that emulates exactly or looks just like the modulating signal. And that's real easy to detect. The bottom half also does that too, but it's out of phase. In most radios, we will just take the top half of that signal and use it. So what do we call the envelope, which is another word for it? We're only going to be using, get the mouse down here, we're only going to be using these from peak to the center line as the signal of interest. So we look at this next one, which has a little better picture, showing essentially the same kind of thing. There's our modulating signal, there's our carrier with nothing on it. When we modulate it, then it looks like the top half of that, as it says here, the AM envelope. The AM envelope is from right along there, from no modulation down to where we can come back up over here at the end. So that is the actual AM envelope. And that's just, I don't know if that helps any or not, but hopefully it will. Okay, What is the modulation envelope of an AM signal? It has to do with peak values, remember? Device A, created by connecting the peak values of the modulated signal to just taking half of that whole signal and take the peak from the top of it down to the center line. What item of test equipment contains horizontal and vertical channel amplifiers?
Oscope.
Got it.
Yeah.
Which of the following is the best instrument for checking the keying waveform on a CW transmitter? Now, when we talk about the keying waveform, we look at the output of the transmitter on this instrument. And when we close the key, we'll see the RF's output signal come up, and it'll go for a short period of time. When we release the key, we'll see the signal collapse. And that's called the keying waveform. What do we use to visually see a signal? Oscope. Okay. What signal source is connected to the vertical input of the scope to check the RF envelope pattern of the transmitted signal? Well, what do you think? We can't put the output of the transmitter into the scope because that'll burn it up. So we have to attenuate the output. So what do you guess? Would you buy D? Which of the following is an advantage of the oscope versus a digital voltmeter? What do you think?
Complex waveforms.
Exactly. The digital voltmeter does not respond very fast as it reads whatever values it's reading, even if it has a simulated meter on it. That way it won't respond up and down anywhere near like the oscope will. The oscope will actually let you see those rise and fall in real time. So complex waveforms can be measured on the scope, and we can't really do that with a digital meter. Purpose of neutralizing an amplifier. We replace the tube in our amplifier. Why do we need to neutralize it?
Eliminate self-oscillations.
You got it. Can't cancel out the spurious capacity that's in the tube. What's the name of the process that changes the instantaneous frequency of an RF wave to convey information? What changes the output frequency all the time in concert with the modulating signal? Called frequency modulation. Frequency modulation, exactly. So what stage in an FM transmitter generates a harmonic of a lower frequency signal to reach the desired operating frequency? You remember we had that lower frequency oscillator there. It goes through a multiplier, then finally gets where it's going to go and goes out the antenna. I just gave away the answer.
Multiplier.
Multiplier. It multiplies by 12 normally. For most today multiply by 12. Total bandwidth of an FM phone transmission having 5 kilohertz deviation, 3 kilohertz of modulation. This is the one I was talking about, Carson's rule, and I couldn't get it to come back up. It's kind of an approximation. It's not an exact thing. We basically add the deviation and the modulation together and then double it. And that gives us 16 kilohertz. So 5 plus 3 is 8 times 2 is 16. And that's how we come up with the answer, 16. Again, that may be one you just want to memorize the answer and not worry about how we got there. Same with this one. Frequency deviation of a 12.21 megahertz reactance modulated oscillator in a 5 kilohertz deviation, 146.52 phone transmitter. Woo. What they're asking is, what is the frequency deviation that we're inputting into that lower frequency oscillator that's going to be multiplied by 12? And you'll remember that as we multiply the frequency by 12, we also multiply the deviation by 12. So if we want to get, if we want to find out what the frequency is at the modulator, we take 1/12 of that 5 kilohertz or divide it by 12, which comes out to 416.666 hertz. So we'd be putting in 416.6, 416.7 hertz into the modulator. It gets multiplied by 12 and comes out on the other side. The frequency would come out 146.52, and the deviation would be 5 kilohertz. Any questions on that? Does that make sense?
Well, as you explained it, it makes sense, but I'm not sure that I've got that committed to memory yet.
I understand, and as I said, this may be one is simpler just to commit the answer to memory. The good part about it is multiple guesses; the answers don't change, so you don't have to calculate it. But I like to know why we're doing what we're doing when we can, and then maybe that'll be one of our review questions that we can review on. Okay, what emission is produced by a reactance modulator connected to a transmitter RF amplifier stage? Reactance modulator there is the key. Reactance has to do with changing the frequency. Actually, I'm not saying it actually has to do with I'm taking it the wrong way. It has to do with the phase, not the frequency, excuse me. Okay, reactance modulator, phase modulation. Process that changes the phase angle of an RF wave to convey information. And that's the phase modulation again, right there. Okay, key there is phase and phase modulation. How is the efficiency of an RF power amplifier determined? Remember that was that little sleight of hand math that we did there. We looked at the output power versus the DC input power to the final stage. Do you remember which one we go? Do you remember which way we go?
No, I don't.
Okay, don't worry about it.
It's A or B.
Yes, it is A or B. You're correct. And I have to stop and think about it myself. If you remember the numbers that we used, we said we had 100 watts on the output. We had 250 watts on the input. So we divided 100 by 250 to get a 40% efficiency. So that says we're dividing the RF output by the DC input, which would be B. Would you buy that?
Yep.
Okay. I don't know if remembering that will help you to come up with that or not. But truthfully, when I get to this one, I always stumble on it. I have to stop and think about it, and that's how I remember it. Okay, output PEP of 500 volts P to P across a 50 ohm load. And there's a funky little formula for that. I do not recommend that you memorize this. I showed it just so you could see it. But the answer is 625 watts. If it's 0.707 times voltage peak divided by 2, all of that squared, divided by the load resistance, which you can see the math worked out there, comes out to 624.82, which is close to 625. So unless you're a sucker for punishment and you really love the math, I would suggest memorize answer B, 625. Okay, we're a couple minutes past 8, and we're at 77 out of, I believe it's 89. Are we okay to keep going till we get finished with this one?
Sure.
Yes, sir.
Okay, we'll keep trucking. What's the ratio of PEP to average for an unmodulated carrier? You remember this is where they are the same. The average power and the peak envelope power are the same if it's unmodulated, which is a 1.0 rate, 1-to-1. Okay, what's the measurement that regulates the maximum power out? Where do we measure the maximum power out first?
PEP out of the transmitter.
And that's exactly right. We always go with PEP, peak envelope power, and it's at the transmitter's output jack. What's the output of PEP and an unmodulated carrier if average power is 1060? Okay, key here is unmodulated. Output and average are the same. So if we get 1060, still going to be 1060.
Yep.
On either side. 1-to-1. What dB change represents a 2x increase or decrease in power?
B.
3 dB.
3 dB, and that's one you just have to remember. Class A amplifier, what percentage of the time does the amplifier conduct? What percentage of the time when it's on does it actually conduct through the final output stage?
100%.
100%. That's why it's least efficient. Which of the following modes is the Class C power stage appropriate for using for amplifying a modulated signal? Now, here, Class C is going to distort like heck. So we know we can't use it for AM. And single sideband is also projecting a modulated voice, so we can't use it for that. What does that leave?
FM.
FM, exactly. The distortion doesn't hurt the FM signal because the frequency doesn't change. Well, the frequency changes like it's supposed to. The distortion does not mess up the frequency, I guess is a better way to say it. Which of these classes of amplifiers has the highest efficiency? We basically just talked about it. The Class C. Which of the following describes a linear amplifier? What do you think?
B, it preserves the input waveform.
Exactly. Input and outputs will be just alike, just amplified. Correct adjustment for the load or coupling control on a vacuum tube RF power amplifier. And the key to that one there is the plate current. Get as much out of it as we can, but we don't drive the plate so hard that we melt the plate. If we drive it up too high and get the plate current too high, it will literally melt the plate inside the tube. What's the effect of plate current on the correct setting of vacuum tube RF amplifiers tuning control? Remember where we had a 3-letter word for that?
The dip.
Get a dip. Get a dip in the current. Purpose of delaying the RF out after activating the transmitter's key into an external amplifier. That's the timing thing, you remember?
C allows time for the well.
Yes.
Yeah, I think it's C.
Yeah, it lets the amplifier catch up. Allows time for the amplifier to catch up, do its switching, do its relays, whatever it needs to do to hook everything up correctly. And normally that's handled automatically in the modern stuff. Hey, we did it. And let me go back and get with you again. I need to. Screen sharing stopped. Okay. Hi, guys. You finished eating, Jeff?
I did.
All right.
Stop.
Hope you had something good.
Spaghetti.
Good enough. Good enough. Okay, we kind of drunk from a fire hose in a way, I guess, tonight again, but I think it was a good choice to go back to the beginning. I really think that was wise. Okay, so we're on this coming Saturday at 6 p.m. Do you want to just go to the next session, which is HF antennas and coax, and then use that last session for review next week?
That's fine with me, Jeff.
Yeah.
Does that sound like a good plan? Okay. And what I'll do for that last session is I think I'll try to go back and excerpt some of the slides that we maybe were a little more complex or we've had more discussion over, and put those in there for the review. And then, of course, you're welcome to bring up anything that you want. Well, if I don't have the answer, I'll look it up for you so we can make that happen.
Can you remind me when you said the testing day was?
It's the 15th, February 15th, Sunday. This
March?
month of February. Yeah, it's coming up soon.
Yeah, I needed to hit the books a little harder then.
February 15. Yep.
Okay.
Get on the online practice test. That's the best thing going. It really is, I think.
It's what I've been trying to do to augment along with your classes.
Yes.
There's certain things that you're going into detail on that don't necessarily make sense with me. And I'm not sure I can still wrap my head around single sideband versus lower and upper, and I don't still understand that. So,
You know, from a very practical standpoint, it might be worth their consideration to do a single class after this is all over and done with, just to talk about concepts. And go back again, start with the AM, and then how do we do, what does single sideband mean? How does that work? And then FM, how does that work? And maybe just see if we can nail it down and make it make more sense. I do better if I understand the concepts personally.
right.
Mm-hmm.
I do as well, so I appreciate that.
Okay, well, we'll keep that one in mind. Maybe we can do it. Maybe well, I don't know. What do you think about the Zoom? Is this working okay for you guys?
Yeah.
It's working fine for me. Yeah.
Okay. All right. Okay. I was before we came online tonight, I was playing with the whiteboard just a little bit to see if I could figure out how that works. I don't know that I'm good enough with the whiteboard on Zoom, but that gives me the opportunity to draw some diagrams or things like that, on the fly. And so that might be one of those places to do something like that. So. Okay, well, this is the end of session number 5, gentlemen. Thank you so much for being with me on this one. And we will see you the next time. Well, actually, we'll see you Saturday for the next session. You guys have a great evening.